So we still prepared exercises for this week. And I'm going to present, I wanted to talk about exercise 103 and exercise 106. Okay, so I don't think I can see the chat, but yeah, maybe somebody can point me then to it. So, okay, let's talk about the whole chapter. So the whole idea in this chapter, circuit compiler, is that you're going to think about the problems that you have now as circuits and as actual mathematical problems that you can put them into a snark. And how you should put them in a snark. So to do that, my colleague Mirko thought about a language actually, which is called paper. It's actually pen and paper, which is actually pen and paper execution rules, where you can very directly put your problem in and see if everything's constrained or not. It has, I think, a quite nice grammar, and yeah, there is different things that I wanted to point out, so you can read about it in the beginning of the chapter 7. So first of all, I think it's really nice that it has this Rust-like structure. The second thing that I wanted to point out is that there is a statement that we're going to have, and it has a list of functions. And we have to have a specific function called main, where kind of the main part of the statement is going to be in. So which is going to be done first, let's say, for the statement. So let's look at the idea. So here's how you would call your statement. Here's the name of it. Then you're going to write down the field that you're going to be in. And then we have to look at the main function, which will take inputs here, where you can, I'll say it as a thing in a sentence. So you will have inputs here and you will have an output. And in here you can set variables and constants, which you will need and or not need. And then you can call other functions, which look like this, very similar to the main one. Which will give an output out, and then you will return what is the output of the statement. So if you use this pub word here, that's the public identifier, so that's going to say that these specific variables are going to be public, and everything else is a witness. So by default, all variables and arguments are going to be witness variables, meaning private inputs, if you don't put a pub specifier in, which would be public inputs then. What else do I want to say about this? Yeah, you can see about the type conversion. You can read about that. So every argument, constant, or variable has a type, and the function is transforming it. So yeah, let's see any other thing that I wanted to say. In general, you can also think about it as having the specific language in general. You should think about this as having a setup phase and a preview phase. So normally the idea is that the circuit compilers, once you set it up, you are executing it to generate the circuit and the rank 1 constraint system, all of that. And then when the prover wants to generate a proof, you actually input, you assign all the instance variables and values. So that's kind of the idea behind this language, and we're going to talk about it for a bit. So let's look at exercise 103. So what is the task? The task is that in F5, so you have five elements, we should brain compile this. So actually, we also describe the word brain compile in the book, but we're going to do it together so you understand what we want you to do. Basically, it means just to understand what's written here and to understand the kind of code the pseudocode that's written here for circuits and what it's doing. And yeah, so in F5 we should be doing that. So let's do it together. So I highlighted a little bit what I thought would be interesting. So we have like, it's called stupid circle. We are in F5, so that's good because we're supposed to do it in F5. And then we're going to jump immediately to the main function and see what inputs we have. They're both witnesses, so they're both private. We have 2 inputs and 2 outputs actually. And we have 2 constants, C1 and C2. They're from the field, so F5, and they're 3 and 2. Okay, and then the inputs are being thrown into the function foo. And then 2 outputs are generated from it. So, okay, let's check out the function foo. So we get 2 inputs also in the function foo and 2 outputs. And here 1 constant is being set. That constant is 3. And then what's happening is an addition and multiplication with one of the inputs, and then an inf thing. So additional multiplication at this point you should be very familiar with. And the inf is something that is a generic idea of things that you would use in a circuit, but we might need to talk about it, so that's why I highlighted it red. So addition, multiplication, normal addition gate, normal multiplication gate, but inf, we have to actually find out what that means. Okay, another thing that I wanted to highlight, okay, let's review inf first, and then I'm going to talk about the other things. So inf is checking that that for x and y, you return the inverse value. So that's the idea. So that y is actually the inverse to x. So it's checking that. So we can look at the paper code for it. So we're inputting 2 variables, outputting 1. So we're outputting the actual inverse. So we're setting a variable xinf, and we're setting a constant, and we're multiplying x and y here, see, and that's supposed to be c, the constant. And so this is a constraint here. And then we're setting y to be x inverse and returning x inverse. So it's checking that actually this multiplication is returning 1 and constraining this. So back to our stupid circle. So what's happening? So one thing to mention here is also that the C1s and C2s from the main part of the statement are not being actually used. So we don't have to actually think about them. And what we can think about is this specific part. So I just wrote it down. So the out1 variable, what is that going to be? So that's an addition here. I just wrote it down for us of in1, the first input, and a multiplication of the first constant, the one and only constant with the first input. Okay, and the second output is going to be the inverse actually of C1, meaning in2. So this is what we are going to be doing. So actually what we're doing, C1 is 3, right? So, and in this inverse function, we're constraining that C1, 3, that in2 is actually inverse to 3. So what we're going to do is, this is how the circuit would look like. The black part is the main function. So as I mentioned, the output 1 is inverse 1 plus 3 times inverse 1. So this is the output 1. And the output 2 is actually the input 2 in case that the input 2 was the inverse to 3. So that's that. So it's not doing anything interesting, but I thought it was interesting maybe to see how this is all working. It's a very, interactive example where you can actually think about circuits and the paper language and how you constrain things and why you constrain things and things like that. So for example, in this specific case, there's no real why we're constraining the input to be the inverse of 3, but the output should be correct. Like we should actually be doing it. So it would be wrong if we wanted to wanted to constrain the second input to be the inverse of 3, it would be wrong to just give it back, right? We need to actually constrain it. So we actually need to use the right constraints for it. Okay, so this was a very basic example. Okay, let's look at the other exercise that I picked out. It's kind of like the other direction. So we're going to have a problem and then we're going to have to write a circuit for it. So it's a little bit similar, but yeah, we don't get paper code. Okay. Sorry, I hear sounds, but I'm not sure people are. There's something in the chat, so let me know. Okay, so let's look at exercise 196. So what is a task here? We have, there's several ones, so I try to highlight them. So we have a finite field, and B and B1 and B2 are two Boolean constraint variables from F. So first, we need to show that the equation for B1, B2 can be the equation where the all between B1 and B2 is actually the same as 1 minus B1 times 1 minus B2. So can you actually write the OR operation through 1 minus B1 times 1 minus B2? As you've seen the OR, like if you've read the chapter, you've seen that we constrain the OR, like how you build the OR constraint is a little bit different. But you can also do it like this, and this exercise is shown here. So let's look at this first. So since we know, like since we have in the setting that B1 and B2 are Boolean constrained, we can actually just write a table and check out all the values. So that's what I did. So B1 and B2, and it's all cases. So if we calculate that out, we see that 0, 0, the result of the right-hand side is 0 as well, and the OR of 0 and 0 is 0 is 1. For the other cases, we know that the OR should be 1. And if you multiply the right-hand side out, we see that we actually also get 1 in all those cases. Okay, I hope you trust me now that the right-hand side here actually proves that if B1 and B2 are Boolean, like so if only these four if only these four cases are existent, then this will actually compute the OR operation between B1 and B2. So I hope that's something you trust me on now. Okay, so let's look back at the exercise. What are we supposed to do now? So we've done that. So use this equation to derive an algebraic circuit with ingoing variables B1 and B2 and outgoing variable OR B1, B2 such that B1 and B2 are Boolean constrained and the circuit has a valid assignment if and only if OR of B1, B2 is the actual OR operation. Okay, so yeah, we're going to use the equation as the exercise wants us, and we're going to have input B1 and B2, and the output should be the OR B1 and B2. So let's draw it up. This is the reminder of right-hand side. So we're going to do minus B1 here plus 1, so that's 1 minus B1 here, and then we're going to do B2 times minus 1, so that's the minus B2 plus 1, so that's going to be the 1 minus B2 here. So we can multiply them together. So that's this part of the right-hand side. And then we're going to multiply this with minus 1 to get the subtraction. And then we can add this to 1. And we get this whole operation. Okay, and the output is then the OR operation, so that should be the output of the algebraic circuit, right? So at this point, I have a question to you. So are we done with this part of the exercise? Is this correct? Wait, I can scroll out a bit. Are you missing something? Is this going to be the OR operation? Is this going to actually constrain the OR operation? So the output that I get, is it going to be the OR, or will it be something else potentially? That's basically the question I have. Since I'm asking in this way, it's maybe easy to see the answer. So since I'm asking in a suggestive way, the output is not necessarily going to be the OR. Yeah, Alf, I think you unmuted yourself. Okay. Cool. Yeah, so this circuit is not necessarily. Oh, hey.
Are we missing the constraint that B1 and B2 are Boolean?
Exactly, yes. Nice. Because, like, can you explain why? Or do you want to explain why?
Well, I think the circuit is fine if we have Boolean values, but for non-Boolean values it could return anything, but not necessarily a value of 0 or 1.
Exactly. Thank you. This is exactly the answer. So since we are supposed to output the actual OR operation, actually have to constrain B1 and B2 to be Boolean, because otherwise we'll get something completely different. Thanks. Nicholas? Yeah, okay, cool. Thanks, Nicholas. Okay, so happy that you all are there with me. So we have to constrain the Boolean. How are we doing this? So can use the statement that something is a Boolean if and only if x times 1 minus x is 0, then x is a Boolean. So this is the sub-circuit, let's say, how it looks. I just screenshotted it from the MoonMath Manual. So if you don't trust me, so here we have x times 1 minus 1 plus 1, which is going to be this part, and then we multiply it with x again, and we have to constrain it to be 0. That's very important. Yeah. Okay, so we can update our circuit with the pink part. So we're going to take B1 and multiply it with the result of minus B1 plus 1, or from here, and the same for B2. So we're multiplying B2 with the result of minus B2 plus 1. We're considering this to be 0. Okay, so this would be the circuit we get. And okay, I don't really hear noises, but yeah. Just unmute yourself in case there is something that you want to say. Okay, so this would be the actually updated circuit, and for this circuit, if we constrain this to 0, if this output, like the sync nodes are going to be 0, then we can actually say that the output is going to be the actual OR operation, and not something else completely. Okay, cool. So that was the idea of this exercise. And then we're going to label it now, because I want to build the R1CS, right? So this is kind of like the idea of the algebraic circuit, but let's label it properly. And then we can also, like, this maybe, sorry, we'll also answer the one from the questions from before, where I think some people had questions about how the labeling should work. Now I see the chat, sorry. So the field elements 0 and 1 are assigned for Boolean circuit operations evaluations. But aren't there some fields when 0 is dropped from the field? Okay, so maybe let's just finish this exercise and then I'll go back to the questions, because I think a little bit easier for all of us. Okay, cool. So let's label the algebraic circuit. I screenshotted a little bit the parts of the MoonMath Manual which are important for this question. So maybe first, like this screenshot on the right. So that's just how to label. So the first 4 bullet points are about nodes. We don't really have to think about nodes in this case. And here, this is about the edges, which we're going to label. So let's concentrate on these 4 parts. So first, okay, all outgoing edges from a node have the same label. Okay. Outgoing edges from a node with a label presents a variable have a label. So that's in our case S1 and S2, because these are variables. Outgoing edges from a node with a label presents multiplication have a label if there's at least one labeled edge in both input paths. So in this case, so I was checking. So let's check this one, multiplication gate. So should I label this outgoing edge from this multiplication gate? And I should not, because we are just multiplying constant. Same goes for this one. And these are addition gates, because we'll come to those, but yeah, they will not have a label. But if we look at this multiplication gate, we see that for this multiplication gate, we actually have in both of those paths, input paths, we have a labeled edge. So we have to label this edge as well. So all incoming edges to sync nodes have a label. So S6 and S5 should have a label because here we are going. We're going into a sync node. So no other edges have labels, and again highlighting about and S4, sorry, S4 is also an edge to a sync node, and S5 and S6 here, since they are going into sync nodes which are constant, they can just be a 0 actually. So just a reminder. Okay, so this is kind of the idea. So just for you to kind of like to summarize it, I think this paragraph is also good. So kind of multiplication of constant is basically not a problem, because in the R1CS we can put that it's going to be in one constraint. So if it doesn't add like new variables or anything to it, then a multiplication is not with constant. It's just basically like it's not going to add a constraint. And also addition, in a sense, is going to be free if it doesn't add a constraint to the system. So if it's also not like if it's not an input to an output gate. So yeah, it's really that's the idea. So I hope this helped. So yeah, I hope this helped for like questions from last time. Okay, so we're going to write R1CS. We're going to want to write R1CS from this, so we have to first write down the constraints. And we'll have a new constraint for each multiplication and for each labeled addition. So we can have a look at of this part. So let's look at S3. So I'm going to write down the left part. It's going to be here. It's going to be one part of multiplication. The other part is going to be the right input path and input graph from that. And another constraint is going to be one of the labeled edges full, which is an addition gate. So we're going to, you can think of this as being multiplied by 1. So here is 1. And this is going to be the right-hand side of this equation. So this is the whole, kind of like this whole part. And then we have these two constraints where S6 and S5 are constrained to be 0. And yeah, this is what we'll end up with. So I'm setting now, this is just the preference that I gave in the setting, that S1 is 2 and S3, so meaning that 2 inputs and the intermediate value should be witnesses, and S4 should be an instance. S5 and S6, as I mentioned, should be constrained to 0. Okay, so from this is the constraint system that we get in general. So I wrote it slightly different. So this is the one part, this is the other part, just the intermediate other witness value, and then we multiply this part with 1 to get the instance value. That's going to be the output. And we have another 2 constraints where we check that these are Boolean actually. Okay, and from the R1CS, we have 1 instance value, 3 witness values, and 4 constraints. And I just wrote down the A, B, and C matrices here. So maybe look at it together. So for the first constraint, we're going to, on the left multiplication here is using the first witness, using it with like the -1 constant and adding 1, so we have to set here 1 as well. And we're doing similar thing for the second witness, so this is the yellow part up here, and the result of this is going to be the third witness variable. For the red one, you see here that it was an addition gate, right? So one of those rows in the matrix, the constant is set to 1, but kind of like no values are actually being used. And the one value that's being used is W3. So yeah, I'm setting here the A, what is it? 0, 1, 2, 3, 4, a 4 value, a second row to -1. And here I'm using the instance, the result, this is the first instance. And for the third and fourth constraint, since the result is 0, we're constraining here, the constant is supposed to be 0 in both cases, and we're using here, like, which one is better to look at? Yeah, I guess we can look at the blue one. So the left-hand side, we're using the first witness here, and we're doing the multiplication here with 1, so that's the blue part here. And just as a reminder, so what we could have done, and that would have been wrong, is to not set these constraints to be 0, the third and the fourth. I've seen people do here, like they just define 2 more instance values. They say we have 3 instance values, for example, and so they're defining kind of like S5 and S6 to be instance values, and they say that this should be S5 and S6 should be 0. This should be S5, meaning I2, and this should be S6, being I3. And here you wouldn't, you would have to have an extra step where you actually verify that these are 0, because otherwise you have not checked that these are actually Boolean. You have just checked that there is some outcome of this computation, and you have to, outside of the proof, like either you check it, like it's not going to be checked inside the proof, if you understand what I'm trying to say. Okay, so this is kind of like how the M1CS looks. Everything else is 0. Yeah, so I think that was it from me. Thanks for listening. So, now going back to the question, I thought it's, yeah, so I think now somebody answered it already in the chat. So, okay, a field has addition and multiplication operations. So you need the 0, obviously, and yeah, I think you can like read maybe more about the chapter on algebra if that's helpful, and maybe look at that again. Okay, so that was that for me. Thanks a lot for joining for these. Wait, there's one more. The main of exercise 1. Why does it say type 2 instead of F? Wait, let me see. 103. Oh, yeah, you're right. So I see what you mean now. Wait, I can go back to sharing my screen so we can all see it. Okay, so this was the task, right? And what Nicholas is referring to is in the main function, we're having 2 output values, right? So we have one field value and one type 2 value. And that's actually a bug. So because we cannot output 2. So since we're returning here so output 2 here is going to come from the output of the foo function. Second output from the foo function. Second output from the foo function is going to be the inverse C1 and inverse 2. And since we did not define it in the exercise, we did not define the inverse function, right? Like I just showed it here from the book. The inverse function actually should be returning a field value and not something else, not a type 2 value. So I think this is a bug, and this should be F2, I think. Hope this helps. Cool. Hey, okay, nice to hear. Okay, so I'll give it to you and to all of you I'd like to study, and I'll stay in the MoonMath Manual chat. In general, if you have questions on auditing, on our audit work, on our audit reports, please ping me. Like, we're always happy to discuss it. Yeah, Chin will take over for the next sessions. Thanks.
Okay.
Bye.
Yeah, thank you, and